I will introduce Laurent, who is probably well known to many of you, but he is the co-director of RISM, the Répertoire International des Sources Musicales in Switzerland, and he is an authority in music encoding, optical music recognition, digital editions, and source-related digital projects. And he is going to be presenting an analysis of musical work data sets and their current level of linkage. So over to you, Laurent.
Thank you. Thanks very much for the introduction. Hi, everybody. I had really hoped to be in Montreal for this, but it's not the case. Hopefully, it's going to be an interesting topic for you. This is work I did with my colleague, Claudio Bacciagaluppi, and it's about trying to understand the situation regarding musical work data sets and as the data sets to investigate the current level of linkage they have. So to give you a little bit of background, as we all know, musical works are a key concept for structuring information. They're a key element to which we can link, and this is of course very important these days in a linked world. However, defining a musical work is very difficult, as we probably all know, and we know that it requires a certain level of abstraction to be determined. So what basically is the work to which we can link and have different entities linking to it. Many institutions have started to create work level authorities. The library world, for example, with the Deutsche Nationalbibliothek, DNB, or the Bibliothèque Nationale de France, they have huge data sets. There are also crowdsourcing initiatives. IMSLP is one of them, and another one which is well known in the Izmir community, Music Brains. And there is also VIAF. People very often refer to VIAF when linking data sets. It was launched in 2013, and since then works have been included in it. I don't know exactly when works have been included, but we have now works also in VIAF. And the objective of VIAF is not to be a curated data set, but more to be a linking point. So it acts as an access point to existing data sets, and it's an aggregation process and performed by a dedicated algorithm. Everything runs at OCLC. So we know all this, but for us, the main questions were basically, what do we have now currently in these data sets, if we want to use them? And also we were interested to know if we can evaluate what's the level of linkage. Very often you look at one of these data sets and say, oh, wow, there was a VIAF, so I mean, might tend to assume that everything is solved, but is it really the case? So that was the background for this work. So the data set we use, DNB, as I mentioned, the Deutsche Nationalbibliothek, also known as KMD, with about 200,000 music works out of about 400,000 works, so a lot of them are music. There are also 5,000 expressions, but we didn't consider them for this work, the higher level, the work level. And that's available as a triple store, so it's very easy for us to use, so about nearly 3 million triples, which we loaded in a triple store. Then BNF started a little bit earlier. So DNB was mostly created from existing data, which was then curated. BNF was mostly the process of, let's say, fiberization of the data, which started in 2011, with now about 170,000 music works. That's also available as XML RDF. So we loaded that also in our triple store, about 4 million triples. Then VIAF, which is a bit more tricky because it's huge. And then we couldn't really extract the musical works. There's no easy way to extract them. So we use basically only the links. That's about 100 meters. And what we did is to look at all the works that had a link towards or from DNB and BNF. And that's about 850,000. And then we basically on the picture, you can see what's available in VIAF when you look at these links. So basically saying this work in VIAF refers to that one. And then we also use Music Brains. It's available as a MySQL, so we could use a dump or PostgreSQL, 1,300,000 works. That was started in 2000, mostly curated by users, and also IMSLP, also curated by users, about 160,000 works. And there's an API. The data is not available, even though it's a community project, so that was a bit frustrating, but there's a very basic, so basically use that to then harvest the data using HTTP requests. So what could we do with that? So first of all, we looked a little bit by composer, what you would get. One more remark on Music Brains. Basically, as you might know, Music Brains is mostly related to recording. So there's a lot of music from composer or musicians from the 20th century. So we cut it down a little bit with a fairly arbitrary cutting points, but by taking composer born before 1920, we ended up with a smaller data set, about 200,000 works. And we also looked at something that's available there and that we thought would be interesting to look at. It's a curated subset. The works are basically listed, work catalog for composers with about 25,000 works. For again, basically you can look at things like that, the first composer or the creator for the BNF, and this is more or less what we noticed. And the first surprise is that, well, there are some cases where there's a high number of works, for example, 2,000, the maximum in the DNB, and about 1,000 in BNF. But if you look at the Q2, which is the median value, it's only 1. So it means that for half of the composer in the DNB, there's only 1 work that's listed. And I think this is fairly low and not necessarily what we expected to see. And this is the case for more or less all the large data set. Only for the curated one in Music Brains is a bit higher, with a median of 21, as you can see in this Q2 column. We looked over time. We could see in the BNF that it's early music, there's a number of works per composer than later on time. And this is the case for most of the data set too. So that was the first finding we had when looking at that. We looked at links. That was a goal of this paper. And basically we could see that for VIAF, there's about 18,000 links. If you remember, we had about 170 in BNF. So more or less 11% from BNF is linked in VIAF and only 8% from the DNB, which is also not extremely high. We looked even further, and this shows basically the links that VIAF has with BNF, with DNB, and in gray that what they have in common. We can see that the library congress is really at the top, with about 50,000 links, so that's not bad. That makes about a bit less than 20% for the DNB. And then there's a huge gap with the next one, the Library of Spain, with 10 times less, about 5,000 works listed there in VIAF. But keep in mind that we use BNF and DNB as starting points, so this can be slightly biased. That gives a little bit of an indication of the level of linkage we have in VIAF. We looked over time. We could take the production date in the DNB or the date for BNF or first year. We also looked at birth date and death date to get an approximate, because otherwise we would have left out too many works, because many works don't have a date. So that means we'll see some peaks, but still that was enough to get an approximation. And for SLP, we could use the composition date, first publication of performance in that order. And this is what we get if we look over time. Interestingly, there are some some surprise if you look IMSLP from 2000, there's really a spike, probably from composer who upload their own work. It decreases in 1920s, so it seems like some people still care a little bit about copyright. If we look at the red and the dark blue, that's BNF and DNB, you can see in the 20th century, they have fairly interesting shape. One is going up while the other one is going down. And all sorts of crossover. 19th century, second half, the BNF is going over and so on. But yes, and you can see these peaks we get because of the publication date. But yes, that's the plot we could do with this data. We look now at these composers, the most works, the 25 of them. These are slightly better mapped with nearly 30% for BNF, so that's a bit better. But what came very interesting here is to see that basically in DNB, there's systematically more works, and for IMSLP and Music Brains, that's twice as many. So this is kind of surprising and interesting, and it seems that there is a difference in what is a work when we look at these data sets. They don't have to have the same view on that. So in order to be able to get a sense of that, we took one composer, because if you do a large analysis, you get these figures, but at some point you need to dig in a little bit. So we took Bach as an example and tried to see what was happening here and why we would have 2000 in the German one and 1000 in the French one. And basically what happens is that this work can be decomposed into sub parts. So this is a broader term, participative in the DNB or aggregated in BNF. And there are up to 3 levels in the DNB and in the BNF. So for example, if we take the example of Das Wohltemperierte Klavier, we have the whole thing as a work, then each prelude, the fugue, and the work, and also in the German data set, each prelude and each fugue as being, even though not all of them, so you would expect to see 48 for the prelude and the fugue, there's only 37 for the first book and even less. So this is not fully consistent. And also, of course, now if we look at the linkage, it's not a super level. So these are not FRBR top level. There's really like large data, large works we group are better mapped with about 30% for BNF and Library of Congress. But then of course, when we go to a movement of a piece listed as a work in the DNB, it's not mapped at all in BNF because it doesn't exist there. And we could also see that if you look at medium of performance, there's some significant difference. I don't know why. For example, keyboard works are mapped to just a couple of %, when others are much better mapped with VIAF. So these all things happening in the mapping algorithm that it's very difficult to understand. And finally, we looked also at what was available in Wikidata. It's very often listed in literature. So there's about 10,000. There's also music works, about 1,000. So we looked at the compositions, and you can see in this table that the level of mapping with IMSLP, with MB series, and with Wikidata remains also fairly low, with 1% for AMSLP, 4% maximum for Music Brains, and 6.7 for Wikidata. So only a few of them are actually mapped. And these illustrate the mapping between Music Brains and MySLP, which is not bad as compared to other cases. So conclusion, as we've seen, we have in the large data set only a couple of works for most composers. This is fairly surprising in our opinion. We have mapping in VIAF that is, we can say, relatively low. The best is between the German one and Congress. And when looking over time, we saw things like the BNF in general more works before the 17th century as opposed to later for the DNB. And we saw these curves crossing over, so this would need further investigations. And as we've seen with the case of Bach, there's a clearly difference in what is meant, what is understood as work between these data sets, with the DNB systematically coming up with a lower granularity with movements. So for example, the violin sonata, all the movement are listed as distinct works. And finally, for future work, of course, we would like to include more data and for example, the Bibliothèque Nationale of Spain also do a deep analysis of VIAF because we didn't have everything there. And I think it would be interesting to look more on a qualitative aspect of this linking, because this focus more on the quantitative one. And that's it. Thank you.
Thank you, Laurent. So thank you very, very much, Laurent. And at this point, I would like to introduce our next speaker, who is Bas Cornelissen. Bas is a PhD student in computational musicology at the Institute for Logic, Language, Computation at the University of Amsterdam, where he is also a member of the CLC Lab and the Music Cognition Group. And he will be presenting Studying Large Plainchant Corpora using Chant 21. And Bas, you should unmute. There you go, perfect.
Let me just share my screen. Is this all working?
Yes, fantastic.
Okay, thanks a lot for the introduction. So yeah, the paper we'll present was very much a spin-off of the Izmir paper we presented on mode classification in Plainchant. And during this project, we realized that there are some amazing Plainchant resources out there that are can be fantastic for computationally minded researchers. So basically, we wanted to make that a little bit easier. And in this paper, we're studying large Plainchant corpora using Chant 21. So unpacking that, we present two corpora, both repackaging existing databases, the Cantus corpus and the Grigo base corpus. We also present a Python package that can convert these formats, GABC and Volpiano, to Music 21, which I suppose everyone has probably heard of, the go-to tool for symbolic musicology in Python now. And as for the studying, we present two case studies, one on the melodic arch in Gregorian chant, and one on the connections between differentiae and antiphons. So I'll go through this quite quickly to leave some time for the case studies and hopefully also for some discussions. So let's start with the Cantus corpus. Yeah, as I said, this is repackaging an existing database, the Cantus database, of course. Which I assume most people here know. This is a vast online index of medieval manuscripts collected by chant scholars over the last decades. And their vast efforts have also resulted in transcriptions of over 60,000 melodies in the Volpiano format. So this is essentially a typeface where you just type plain text and this is rendered as notes on 5 staff lines. So it's a very easy format to work with, developed specially for chant, notating chant. But it uses a modern notation, 5-staff notation. And the second corpus we use is the Grigo base corpus, and this uses a different type of notation. Again, this is also repackaging an existing database, Grigo base, a website where people have collected transcriptions from modern chant books, basically. There's over 9,000 melodies in there, all written in a format called GABC, a different chant format, and this was developed for typesetting chant in square notation. So square notation uses 4 staff lines. I won't go over it here, but one thing to note is that it's a very elaborate type of notation where you have all sorts of niceties, such as rhythmic signs, different note heads, epicema, liquescence, flat clefs, what have you. So this is really an elaborate notation, and it is intended for performance. So these two corpora, if you like, give two complementary perspectives on chant. On the one hand, we have the Cantus corpus, which contains medieval music collected by and for chant scholarship. for chant scholars, I should say, in a simple format for piano. And the Griego-based corpus is really a modern reinterpretation of the repertoire in a very elaborate format intended for performance. So I can imagine that they can serve very different goals and maybe help answering different types of questions. Okay, these corpora, these databases exist already, but working with them in, say, Python or in Music21, one of the standard tools nowadays, is not always so straightforward yet. So that's why we developed this library, this package, Chant21. So the main thing we wanted to do when we built Chant21 was to preserve the structure of a chant. So by that I mean the way it is divided in sections consisting of words, which in turn consist of syllables and neumes. And the reason we thought this was important is that in chant, of course, text and music are very closely intertwined. In our ISMIC paper, we also found that this really can help in computational studies to use the textual structure of the music. So we wrote converters for GABC and vol piano that keep this structure intact. So they produce a hierarchical representation of the chant. So a chant divided in sections, words, syllables, and neumes. One additional benefit is that we can then quickly visualize both the chant and also its structure in Jupyter notebooks, as is also illustrated on the right. And this is very useful when working with these vast data sets to quickly inspect what they look like. I'll show more of this in the demo after the talk. Now, just so you know, there are some related converters. Music21, of course, has support for vol piano. And it even contained a GABC exporter in the past, apparently. And there are some other converters out there, but none of them preserved the hierarchical structure we were interested in. And also the text alignment for vol piano was particularly important for us. As for the implementation, we did this using custom grammars, but I won't go into that here. So for more info about the library, I really refer to the demo afterwards. Okay, so we have two corpora and we have a Python package. Now what can we do with this? So I'll present two case studies, and the first concerns the melodic arch. Now, as you may know, the melodic arch hypothesis claims that phrases in songs tend to be arch-shaped. David Uren famously showed this in 1996 using the Essen folk song collection. And after that, it's been shown in a number of other folk song corpora, and as far as I know, there are no computational analyses of Plainchant. So we thought it'd be nice to see if we can also find a melodic arch in Plainchant, in Gregorian chant. So we used the Griego-based corpus, and one nice thing is that GABCs, or the square notation, uses pausas, these little signs over here, to mark breathings. And we can use these to easily extract all the phrases. So we take a melody, we extract phrases by looking at the pausas, and then we convert each of the phrases into a kind of standardized contour representation. So if you look at the figure down here, then it's probably easiest to see what we did. In red, you see a kind of piano roll for all of the notes in the first phrase, and we sampled 50 pitches across the phrase, equally spaced, and we normalized them so that in duration, so that position 0 is always the start of the phrase and position 1 is always the end. And then we also transposed the whole phrase so that the mean pitch of the whole phrase is 0. This is similar to what some other people have done and turned out to work well. We also tried some other normalizations. Okay, so for every phrase we now have a standardized contour representation, but to see if those are meaningfully arch-shaped, we also wanted a kind of baseline, a comparison. So what we did is we again start with a melody, but now we're going to segment it randomly. So we randomly pick segment lengths. So we randomly sample the length of the first segment, say 4 notes, or 1, 2, 3, 4, 5 notes, and this is what we end up with. The length of the second segment, the third, the fourth, and so on. But we do this in such a way that the lengths are roughly the same as the lengths of actual phrases. And also we'll discard the first and the final phrase, or random segment, just to make sure that the overlap with actual phrase boundaries is as low as possible. So what this results in is a set of random segments that are very unlikely to overlap with actual phrases, but are still roughly of the same length. Okay, so now we have a random baseline, we have our actual contours, so are they arch-shaped, is the question. I'll show 4 genres: antiphons, hymns, introits, and responsories. I'll show the pitch of the contour vertically, and horizontally I'll show the position in the phrase. And now every contour is basically a set of 50 pitches, and we'll just average all the pitches at position 0, all the pitches at position 1, etc. So we end up with an average contour, the average contour of all antiphons, say. This will be shown in color, and in gray we have the random baselines. So there we go. I think visually it's kind of clear that these are arch-shaped. So all the colored lines correspond to actual phrases, and they're clearly more arch-shaped to the baselines than the baselines. And I think that's an important point, because it kind of shows that the arch-shaped you see in the colored lines in the actual phrases is to be explained by how the phrase boundaries are positioned. Because if you were to move them, like you do in the random baseline, you lose the arch, you destroy the arch structure. So, yeah, just to keep it short, I think we can conclude that in all these genres, the phrases tend to be arch-shaped. There's much more to be said about this, but I leave that for discussion or for future work. So the next case dives into a much more specific problem from chant scholarship, which was also discussed at this present conference a few years ago. Namely, the connection between differentiae and antiphons. So Rebecca Scholl presented a paper about this in 2018, and we basically revisit that work. So an antiphon is always, that's a type of chant, is always performed together with a psalm. So the way you do this is you first sing the antiphon, then after that you sing a psalm to a standard recitation tone, and you end this with the words Seculorum Amen. And this part of the psalm is called the differentia. And after that you again sing the antiphon, so you repeat the antiphon. And the question people have asked, and people are apparently also divided over, is whether the connection between the differentia and the antiphon is somehow systematic. A different way to put it is, do certain differentiae imply certain antiphon openings, or is the connection between these two non-existent, and are they kind of random? Is there no connection whatsoever? So the way we'll investigate this is as follows. We extract the last 6 notes of the differentia and the first 6 notes of the antiphon, and we concatenate those to form what we call the connections. And we'll number the notes in the connections in such a way that position 0 is always the opening of the antiphon. That's just convenient. So using now not the Griego-based corpus, but the Cantus corpus, we extract connections from 7,000 antiphons. And what I'm going to do on the next slide is basically just plot them, just show you what the connections look like. So there we go. I'll show 2 modes, mode 5 and mode 6. I don't really have good time to explain what modes are, but I think in this audience that's a safe assumption to skip this, I hope. So vertically we have the pitch, again, and horizontally position. Remember, position 0 is the start of the antiphon, and on the left we have the differentia. Okay, so this is what we get. And every line, so you see some very thin lines, corresponds to a single connection. I've jittered them vertically so you can see overlapping lines, how they cluster. And what you can notice is that, for example, in mode 6 on the right here, the connection, which is the part shown in black, is pretty systematic. So there's basically only one differentia used, and it always results in the same opening note of the antiphon. So this is a very predictable transition, a very predictable connection. Whereas in mode 5, there's more differentia used, but still there's one big cluster, the thick green line. But this connects to 3 different openings, so a less systematic connection, or less predictable, if you like. So in a way, this already answers the question of the second case study. And the answer would be, it seems to depend on the mode. So just looking at these plots, it seems to be the systematicity of the connection seems to be different across modes. So one more thing we tried in this case study is to see if we could also quantify the systematicity. And the intuition is basically that these connections are more dispersed than these connections over here. And we could measure this formally by computing the entropy of the distribution of all these connections in both cases. So we think of this as a measure of the dispersal in these red blocks. Now, if we do these computations, I can tell you more about it if you're interested. We indeed see that the entropy is higher in mode 5 than it is in mode 6. So again, this means that this connection is more predictable than this connection, more systematic than this connection. As you can already see, we did this for all the modes, and we actually did a little bit more. We also tracked how the entropy changes if we move across the chant. But I won't go into that for now. Please refer to the paper if you're interested, or ask me during the demo session. For now, our answer to the question, are the differential antiphon connections systematic, depends on the mode. I'll leave it at that. Thanks for your attention. Or maybe just point out that all the corpora are of course online, as is Chant 21, the case studies as well. And if you're interested in mode and chant, do also check out our ISMU paper.
So with that, I would like to introduce our next two speakers. So Jeremy Sawruk is a software engineer and composer specializing in artificial intelligence and music notation. He currently works at Facebook AI Applied Research and is actively involved in the W3C Music Notation Community Group. And we also have Jacob Walls, who is a developer at JW Pepper and a PhD candidate in music composition at the University of Pennsylvania. And they are going to be presenting personalized sheet music search.
All right, thank you. Can you all see my slide? Yes, great. Okay. So we are presenting, our paper is called Personalized Sheet Music Search. So here's the problem. How can performers find sheet music? It's really difficult right now, and it's even more difficult when you have an ensemble, and it's even more difficult when that ensemble is K through 12 education, where the ensemble is constantly changing. So there's a lot of sheet music, a lot of different arrangements of the same compositions. How do you find which ones work for you? Well, the traditional method is you'll go into a store and you'll just browse through, and say, okay, that looks good. That's time consuming. If you go online and look at digital retailers, you'll see that publishers will often limit the number of pages you can see to only a handful, which doesn't give you the entire picture of the piece of music. The end result of all of this is that you end up having a limited, narrow standard repertoire. The same pieces get played over and over again. So how can we improve this experience of finding music? So let's look at some of the ways that we could find sheet music today. The first way is through text-based search engine. Those only search for metadata such as title and composers and keywords. There can be very incorrect results in there, and any of the information that you get back is very vague, particularly in regards to difficulty. Again, there might be multiple arrangements, and it might say, this is for a middle school choir, but is your middle school choir good enough to perform that is a different question. So they are very limited in scope. Another potential search solution is a motif-based search engine. Those are great if you already know the melody you want to find, but aren't particularly useful for music educators because they're more interested in, can my students play this? So while tools like PeachNote or Music 21 are great for researchers at answering these types of questions, they just aren't particularly effective for educators. So the solution we proposed is a profile-based search engine. The central concept is we create a profile of an ensemble. An ensemble contains one or more instruments, and we want to combine for each instrument the skill level so that we can search by skill level on a per instrument basis. We can also set ensemble level parameters that would apply across all instruments, such as key and meter information. We will then use that profile to search against a database of composition metadata. This way, music educators can find compositions that match the ability of their ensemble. And because it is not connected to anything except the metadata, that can help surface compositions by lesser known or underrepresented composers as well. So here's an example screen of putting together what a profile looks like. Jacob will be hosting interactive demos during the demo session, so you can check that out if you want to see this in action. So what we have here is we can set up a profile in the advanced search page. Here we have a concert band that's already preset for us. There's a drop down here where you can select some pre-made ensembles. You can select a predetermined level, or you could change the level for each instrument. These represent the ranges. Right now, in the current implementation of the search engine, we are limiting the search to range, even though we are collecting more metadata than just that. You can click on this thumbnail and bring up an editor to change the range of the instrument. And then when you're set, you can click search by range. That will then search the database and find all of the compositions that match the profile you've created in this search interface. After you've run your search and you come to the information page about the composition, you will see the range information displayed. Here we have range information for what appears to be a concert band composition. As you can see here, we have a flute part where the lowest note in the flute part is A flat, and the highest note is C. These small red notes that are bracketed represent the tessitura, which should be the most common range. This is particularly important in the world of choral music. We define the tessitura as plus or minus 1 standard deviation from the mean pitch. Another thing to note about this display is that all of the pitches that are displayed as written. So this is, as the performer would see it on their sheet music. We also take the names of the instruments here are as they appear on the score, but the search engine, when we extract the metadata, normalizes those names to a standard set of tokens that makes it easy. So if you just search for clarinet, we will match on clarinet 1, clarinet 2, B flat clarinet, etc. For unpitched percussion, obviously there is no range, so we don't display the range, but we do list the percussion because directors are often curious about what they will need in their percussion. And other instruments such as timpani here do not have tessitura because that concept, it does not make sense. Piano would be similar. It's not as important as it would be for vocal or wind instrument. So how do we get this metadata? There are a couple of ways we could approach this problem. We could do human annotation. That would be extremely time consuming and impractical. We did some timing analysis with experts who could do it pretty quickly, and it still came up to just be an impossibly large amount of time to do it. So that's probably not an effective way to do it. We could use OMR that already exists, and that could be very useful, especially for individual parts. What we have found is that when we're running at scale, when we're processing thousands of compositions, there are just simply too many errors for it to be reliable to work at scale, even if it might work for a small number of compositions. If we were processing it, we would probably just use OMR on individual parts and avoid scores altogether. But oftentimes, especially in choral works, we only have the score. Another solution that I proposed is what I'm referring to as fuzzy OMR. This is OMR that looks at a piece of sheet music and makes semantic determinations without having to identify each and every note and glyph. In this case, we can look at a measure or a staff and identify the highest note while not considering any of the other notes in that staff. That gives us a way that we won't have to worry as much about trying to identify every single item that occurs. There's a lot of research that remains to be done in that area. Finally, we can use Music XML, which is the gold standard because that contains all of the notation information we would need, such as the actual spelling of the pitch, the rhythmic duration, etc. The biggest problem with that is that the corpus is very limited, and music publishers are often unwilling or even unable to provide Music XML files, often due to copyright concerns. So to address that, we've created two plugins, one for Sibelius, written in manuscript, and one for Finale, written in Lua. By using these plugins, publishers can just run the plugin inside their notation software, and it should not disrupt their workflow. And we will get the data that we need for the search engine, and they can continue to hold on to their existing master Sibelius Finale files. The last thing is we've developed our own PDF analysis engine, which looks at vectorized PDFs and looks at the geometry and glyph information to determine musical semantics. It's not as accurate as Music XML, but it's very close. Unfortunately, this algorithm is proprietary, so I can't discuss this in particular detail at this time. So this currently exists in a limited form. JW Pepper has adapted this into a system called MINT's Music Insight Technology System. It's indexed on 16,000 band, choral, and orchestra titles. You can go in and see the range information, but the search functionality does not currently exist. It is free, but it does require a login so that our site just doesn't get scraped. And you can find the login information here. And certainly, stop by and we'll be happy to demo it for you, including the search engine during the demo session. Next steps. We want to work with publishers to supply more metadata. That's going to be an ongoing thing. We would also like to research ways of getting more complex metadata. For instance, how can we model rhythmic difficulty? That's something that band directors are very interested in. Can we create an open interchange format for the metadata that would be exported from the notation programs and input into our database? And is that a standalone format, or is it an extension to MEI or Music XML? We also would like to investigate ways to integrate this metadata with more tools, whether it's music education tools like Smart Music or non-commercial use cases like IMSLP. Thank you for your time.
David Weigl is an interdisciplinary researcher in cultural and social informatics at the University of Music and Performing Arts in Vienna, Austria. His research focuses on the application of semantic web technologies in the field of digital musicology. He is also the data officer of Trompa, the Trompa project, which we've been hearing lots about already. So David will be presenting read-write digital libraries for musicology.
Thank you very much. Let me attempt to share my screen with you. There we go. Wonderful. I'll attempt to be quick. I'm David. I'll be talking about read-write digital libraries in the musicology context, part of the work we've been doing in Trompa. And we are going to start with Tim Berners-Lee. Tim Berners-Lee sitting in front of a computer in 1990 at CERN. On the screen of his computer, you can see a web browser. In fact, you can see the web browser that existed at this time. It's called World Wide Web. And in an interview 15 years later, he was saying that the idea was that anybody who used the web would have a space where they could write. And so the first browser was an editor. It was a writer as well as a reader. That's quite interesting. This is what it looked like. Pretty modern, I think. As we can see, it is indeed an editor as well as a browser, which is cool. In fact, you could do a WYSIWYG HTML editing with this thing. It's kind of mind-blowing to me. But it ran on Next. So this machine he's sitting in front of is a Nextcube, and it uses the NextStep operating system. This was the bee's knees of personal computing in 1990. The more sort of widespread computers looked like this. And this is the second web browser called Line Mode. And it was implemented by Nicola Pello, who was a colleague of Tim Berners-Lee's at CERN, who also helped in the implementation of the first browser you saw. And due to limitations of the platforms at the time, this was a passive browser. So this could still read the web, but it couldn't write to the web. Now, around this time, graphical user interfaces did become more in vogue. And so we start seeing these things, the predecessors to the browsers we use today, but they were also passive. So they're graphical, but the main focus of these browsers was to read the web, not to write it. Let's shift briefly to digital libraries now. So as in the web, an early focus of digital library work was also on writing as well as reading. Now, this is a paper from 2006. I'm not claiming that this is the beginning of digital libraries. Of course it isn't, but it is quite a while back. And this is a very far-sighted paper. It's called Beyond Digital Incunabula. And the main core message of this paper is that it's not sufficient to provide digital versions of static print libraries. That misses the affordances of the digital. There's more that we can do with digital libraries. And so they outline these three features that characterize successful digital library design, according to them. One being finely granular collection objects. So you don't just point to the volumes in your collection, you point to fragments of information within those volumes, meaningful fragments of information. Then they talked about automated processing. So that's feature extraction from your collection or classification, machine classification. And then indeed, they're talking about decentralized user contributions. So the users of your collection are providing contributions. They're not just reading, they're also writing. That brings us to Trompa, towards richer online music public domain archives. I won't say too much about this project right now, partly because I already talked about it last year. So do feel free to look at those slides from last year. But very briefly, the project is about interconnecting and enriching public domain repositories of music information on the web for a whole variety of different use cases, and with the intent that the users of these use cases are able to provide contributions to enrich this data, and that those contributions are useful to everybody. How do we do that? Well, this is the core of the Trompa DL infrastructure. It's a knowledge graph. It's a graph database that sits in the middle and connects various repositories of music information on the web. Hooked into this is a processing library, which monitors the graph for updates. And when a new node pops in, it sees if it runs filters to see if it can do something about them. And if it finds a node it's interested in, it runs algorithms, for example, feature extraction algorithms, and they then publish their results back into this graph. Right, but how do we handle user contributions? Now, the P in Trompa stands for public domain. We're in the business of providing access and enrichment to public domain music resources. Now, we can't demand of our users that everything they do for us becomes immediately public, because then we have no users. Nobody would want to do that. We want to make sure that the users retain ownership of the data so that they can decide what happens to the data. On the flip side, we don't want to be liable for GDPR safeguarding. So GDPR, the data protection regulation, guarantees, for example, the right to erasure. That would mean that users are allowed to demand that all of their personally identifying information is removed. That's a massive administrative overhead. We're not in the business of doing that. So we limit ourselves very much to public domain things in our collections. So how can we still provide for user contributions? Let's go back to Sir Tim. So he talked about this idea of having a space. The users of the web should have a space where they can write. So he thought about this for quite a while. And in more recent times, here's a photo of him last year at a conference in Cologne. He's come up with a solution, him and various colleagues, of course. So here he's now sitting in front of a Mac, no longer a Next Cube. It's covered in a lot of stickers, including this one. This is the Solid project. Solid is a web decentralization project that basically provides that space to users in the form of so-called solid pods. Those are personal online data stores. And they're basically little bubbles of link data that every user is able to write to. Everybody has their own pod. And the pod gives you one space to write into, but also two, it acts as an identity provider, which means you can use your pod address to log in to applications that buy into this ecosystem of Solid. Right. How does this work in practice? Well, I have a demonstration of a musicological annotation interface we've built in Trompe. It's hot off the presses. This was implemented by Federico Zubani at Goldsmiths with a little bit of help from other colleagues. And I've got a video here to show you. You can try it out yourself as well. So we're logged into one of these pods, the Trompe demonstration solid pod. I can specify a place inside that pod, for example, the public folder. I can load any MEI file on the web, for example, this one. And I can fetch the annotations that I have already made in my pod about that MEI file. So I've got two here. I can click on an annotation to see it highlighted. I can hover over it to see a textual description. This didn't get picked up in my screencasting software, sorry. But imagine a tooltip that says the textual description popping up. And of course, I can make new annotations. So I have the option of node selection, where I can just click and drag a bunch of nodes. I can press Shift to unselect or to select non-contiguous parts. Or I can do measure selection as well. There we go. And then I can add my annotations. So you've already seen I can make textual descriptions, but I can also put links. So these could be linked data resources or just web documents. And oh, hello, can you see me still?
Yes, we can see you. Mm-hmm. Oh, although your screen
struggling a little bit with my connection, sorry.
Yeah, it may have frozen for a bit.
Okay.
Oh shoot, looks like he's...
Sorry, I appear to be back.
No problem.
My apologies. Let me attempt to come to a conclusion then. So I don't know if you saw the last bit there. So you can click on the annotations that have a link and end up on that page. So in that case, I had the Wikipedia page for Clara Schumann pop up when I clicked on that bit of score that had been annotated. Let me share the screen again. So you saw me enter some annotations into a solid pod there. If you imagine this one in the middle is the one that I was writing to. By default, those annotations are private to me and only me. As I said, the solid pod is also an identity provider, so I have a means of logging into this pod and seeing the annotations. I can choose to privately share them with other solid users using their identities. I can, of course, choose to make specific annotations public so that anyone on the web can read them. Or I can decide to publish them under an open license to a digital library, such as Trompe's interface. Now, at the point where I as the user specify, for example, a Creative Commons license for my annotation, that annotation is now no longer personally identifiable information in the GDPR sense. That annotation is now a publication in the public domain. And at that point, Trompe becomes very interested and happy to incorporate that into our collection. I am probably overrunning, so I won't talk much about binary file storage, except to say that these solid pods, in principle, can house any sort of data you want to throw at them. In practice, most of the providers for pods, if you're not hosting it yourself, don't emphasize huge storage spaces at the moment. So right now they're really intended to house mostly linked data resources. But if you have large files like videos or audio files that are interesting to musicologists, you can of course store them anywhere else on the web, because it's all linked data, it's all the web. So you can just point to URIs in institutional repositories or at cloud hosting services. One interesting alternative is distributed storage, such as IPFS, that's the Interplanetary File System. We talk about this briefly in the paper. It's basically a peer-to-peer network similar to BitTorrent or Napster back in the day, and it provides a means of hosting content without having a sort of central server looking after it. But there's more on this in the paper. So I'm going to conclude here with an overview slide of the architecture that we're proposing in the paper and that we're working towards in the Trumpet project. So here you have Alice's pod in the middle. Alice provides a contribution into her pod, so that could be one of the annotations you just saw. That could, for example, be a piano performance in one of Trumpet's other applications that I showed in the demo session earlier. That goes and lives inside Alice's pod. It can be private to Alice. It can be authorized to specific others, like Bob. It can be made publicly readable to the wider web. It can include large files like audio recordings that can live anywhere on the web. And it can be published to a digital library or to more than one digital library. An advantage of having this data sitting in this user-controlled space is that you sort of get around this data siloing problem. All sorts of different collections can refer to this contribution. We've come up with two different ways this publication could happen. One is the announce model, where a digital library just includes a URL for the contribution pointing into the pod. So they're announcing that there is a contribution here. The other is the ingest model, where the contribution is copied into the collection of the digital library, and a provenance attribution can still be provided pointing to the original source. That is where I will end for now. Thank you very much for your attention. Here's a few demos to try out.
Thank you, David.